Ever wonder how hackers hide their tracks in plain sight on a Windows machine? Or how forensic experts uncover digital footprints using nothing but command line tools? In today's deep dive into Chapter 5 of the Guide to Computer Forensics and Investigations, we'll explore exactly how Windows systems store critical evidence, and how you can uncover it. Before we jump in, hit that like button, subscribe, and tap the bell icon so you don't miss out on future forensic breakdowns. Let's get into it. Windows is the most widely used desktop operating system, making it a critical environment for forensic investigations. When a crime involves a Windows machine, which it often does, you need to understand how data is stored, managed, and retrieved within its file systems. You also need to be proficient in both GUI and command line tools to conduct thorough and legally sound investigations. Windows primarily uses FAT, File Allocation Table, and NTFS, New Technology File System. FAT was designed for smaller drives and is often seen on USB flash drives and legacy systems, while NTFS is the modern standard for Windows hard drives. In FAT, clusters, combinations of sectors, are numbered starting at 2. NTFS starts at 0, and adds complexity and functionality with features like the Master File Table, MFT. The MFT is essentially a relational database that holds information about every file on the system, including timestamps, file paths, and metadata. One of the key forensic tasks is understanding how to interpret and reconstruct timelines based on this metadata. NTFS supports alternate data streams, ADS, which can be used to hide data within a file. This is often exploited in malware or data exfiltration. Knowing where and how to locate these is a vital skill. Understanding the Windows startup process is also critical to digital forensics. The BIOS, Basic Input-Output System, or in modern systems UEFI, Unified Extensible Firmware Interface, loads the bootstrap program from ROM. This process initializes the OS and prepares the system for use. However, this startup can also alter evidence. That's why forensic investigators use bootable USB drives or CDs configured to prevent changes to the original drive. These tools allow you to boot into a safe environment where evidence can be imaged without contamination. The physical layout of a drive is divided into partitions. These logical units allow multiple OS installations or data storage areas. Hidden partitions, often left by system manufacturers or used to conceal illicit activity, can contain vital evidence. Tools like WinHex allow forensic examiners to view and interpret the raw hexadecimal data on a disk, including these hidden or unallocated areas. Solid-state drives, SSDs, present unique forensic challenges. Unlike traditional spinning hard drives, SSDs use flash memory, and they incorporate wear-leveling algorithms to prolong device lifespan. These algorithms constantly move data across memory cells, which means deleted data may be quickly overwritten. Furthermore, SSDs may support trim, a feature that proactively erases deleted blocks, complicating recovery. For this reason, capturing a forensic image of an SSD as soon as possible is critical. Flash memory is also found in mobile and embedded devices. These retain data in both allocated and unallocated space through a small internal power source, which makes them volatile and time-sensitive from an evidence preservation standpoint. The Windows Registry is a centralized database containing configuration settings, user activity logs, and system information. It is structured into hives, each corresponding to different parts of the system. Keys and values in the registry can reveal when software was installed, what USB devices were connected, what files were accessed, and even what websites were visited. Tools like Regedit or third-party viewers can help parse and interpret this wealth of information, making the registry an indispensable source during investigations. While graphical user interfaces, GUIs, are user-friendly, forensic professionals must also be proficient with command line interfaces, CLI. CLI tools offer precision, speed, and access to deeper system functions. Commands like ipconfig can show network configurations, netstat reveals active connections, and dr helps browse directories, even hidden ones. You can use regquery to pull information directly from the registry. These commands are especially valuable when operating in a restricted environment, or from a forensic boot image. A powerful technique for safe examination is the use of virtual machines, VMs. By imaging a suspect drive and loading it into a VM, you can explore the system in a controlled, isolated environment. This allows for deeper analysis, behavioral observation of malware, and testing without modifying the original data. Tools like VMware and VirtualBox support mounting forensic images, and advanced configurations even allow for snapshotting and rollback, which are useful when testing volatile data or system changes. In summary, Chapter 5 arms you with a comprehensive understanding of how Windows operating systems manage data, and how you, as a digital forensics examiner, can effectively analyze, extract, and interpret that data using a combination of graphical and command line tools. Understanding file structures, boot processes, drive architectures, and the registry can mean the difference between a breakthrough and a dead end in your investigation. If you found this lecture helpful, be sure to like, comment, and share it with your fellow students. Subscribe so you don't miss the next module, Chapter 6, where we break down forensic tools in greater depth. Until then, keep learning, keep questioning, and always stay forensic.